Bonjour, buddies. Welcome back to another video. Today's first question is, well, no, not today's first question. It's our description. In this problem, we show that the square root of 2 is an irrational number, which means it cannot be expressed as a quotient of two integers. We will use a powerful technique called proof by contradiction. We start by mentioning that we can write the square root of 2 as a quotient of two integers, and then show that this leads to something impossible. Number 1. Suppose that we can express the square root of 2 as the quotient of two integers. We can express any quotient of two integers in simplest form, which means that the numerator and the denominator have no common factors greater than 1. So we suppose that there are some integers p and q for which the square root of 2 is equivalent to p over q, and p over q is in simplest form. What must the square of p over the square of q equal? So this problem is just like the prelude of everything else. Whereas if the square root of 2 is equivalent to p over q, we can square each side to get 2 is equivalent to the square of p over the square of q. And this is pretty simple, it leads right to that. So that means that this is equivalent to 2. Our first problem is equivalent to 2. And you should probably keep this in mind because it will be useful in the later problems. This is more of just like the leading up. Alright, problem number 2. Explain why p must be even. So now that we've already proved that p squared over q squared is equivalent to 2, we can move q squared to the other side to isolate our p. So this means that p squared is equivalent to 2 q squared. And this basically shows that p squared can be written as something with a factor of 2 within it. And since only even numbers times even numbers are equivalent to even numbers, and odd numbers times odd numbers are equivalent to odd numbers, but that isn't really relevant here. But mostly because of this. Since even numbers times even numbers make even numbers, and nothing else can create even numbers, this means that p is also even, just like p squared. And this is also just sort of like, you'll see at the very, very end. It's sort of like a revelation. Question number 3. Since p must be even, there must be some integer r such that p is equivalent to 2r. Use this to show that q must also be even. And this is where things start getting a little wonky. So if p squared is equivalent to 2q squared, like we said in the previous problem after breaking it down, and we can replace p in this case with 2r, since it did deem p is equivalent to 2r. So if we do this, we don't know if r is even or odd. It can be either, but that doesn't really matter in this case. So 2r squared is equivalent to 2q squared. And if you guys are like mathematically good, you might already be able to see, or experience basically, you might already be able to see ahead of the future steps. But if we bring the square into our parentheses, we will get 4r squared is equivalent to 2q squared. And if we divide both sides by 2, we'll see that 2r squared is equivalent to q squared. And you can also see that this situation is kind of similar to the one we just got above, with 2r squared is equivalent to q squared, and p squared is equivalent to 2q squared. So this means that q is also a number that can be split in 2, which also means that it's even because it does have 2 as a factor inside it. And using the property that even times even, only even numbers times even numbers are equivalent to even numbers, this q is also even. So now that we've proved all of this, why are we proving all of this? In the previous 2 parts, we showed that p and q are both even. Why does this contradict our setup in the first part? Why does this tell us that the square root of 2 is irrational? So, if p and q are both even, that means that they share the factor of 2. But if this shares the factor of 2, this means that if p over q is in simplest form. However, a simplest form means that they have no other factors besides 1. So this means that if both of them are even, they share the factor of 2, which means that P and Q are not actually in simplest form, which starts contradicting our first setup, which is saying that P and Q are in simplest form. A number cannot be in simplest form and not in simplest form, which means that the setup that they assumed in the beginning, so if they suppose that there were integers P and Q for which the square root of 2 is equivalent to P over Q, and P over Q is in simplest form, their starting setup slash supposing slash assumption is incorrect, which means that square root of 2 is irrational because it cannot be written as two integers over each other that is in simplest form, which all rational numbers can do. So just a big line of proof here. It's sort of just like a leading up of each other, sort of. But yeah, that's the end of this video. I hope you guys enjoyed and I hope you guys learned something new. And I will see you all on the next one. Bye!